last chapter in this course, which is on differential equations. So this one is not as long as integration, but it is a little bit longer than matrices. But I think in 2 weeks, hopefully by Friday, next week Friday, we should be done. There's only a few types of differential equations that we're looking at. We're not going too deep. It's only first order differential equations. And I think there's like 3 or 4 types that we look at, and then we are done. So remember, on Friday, you have test 3. That's on matrices. Yeah, so prepare for that one. Okay, so let's get started. I'm looking at this is on differential equations. So you have seen these before. Even when we were dealing with differentiation and integration, we looked at some of them, except we didn't solve them. What we did was just verify that that equation was the solution to a differential equation. So with these differential equations, this is an equation in which derivatives, I need a new pen, in which derivatives of any order of a function y is equal to f of x occur. Okay, so that is what I said about matrices is that that is what the test is on. This Friday you have test 3, I believe that's in the course outline, and test 3 should be on matrices. Okay, so when you have equations where derivatives of any order of a function appear, that is what we call differential equations. So we can look at some examples of these differential equations. The first one, we have d2y dx2 plus 2y is equal to 0. So this is a differential equation because you can see this is the second derivative of y, and it appears in this equation. So what we want to do here is find an equation that when you differentiate it twice and then add 2y to it, the answer is going to be equal to 0. So some of these, even just by thinking, you can come up with one. So maybe this one will involve something to do with sine, because we know sine, if I differentiate it once, I get cos. I differentiate it again, I get sine. I'm back to sine. So just playing around with that plus, minus, or sine of something, or yeah. So you can imagine that this might have something to do with sine or cos. Okay, or maybe e to the power of something. Yeah, but again, we do have techniques that we use to solve it. It won't just be guesswork that you have to use to solve them. But this is an example of a differential equation. Another one, we have dy dx y squared is equal to 0. Here we have the first derivative multiplying by y squared is equal to 0. So we have to find a function that when I differentiate it and then multiply it with the square of the function, I get 0. Okay, then another one, this is number 2. And number 3, we have d3y dx3 plus 3 dy dx is equal to y. So again, this is what it can look like. The third derivative plus 3 times the first derivative is equal to the function that you started with. So we're trying to come up with a function. You differentiate it 3 times. You add 3 times the first derivative, the answer is equal to the function that you started with. But we will not work with equations like this. We will stop when we have dy dx. So we won't go into higher orders, but it's good to know what this means. This just means we're looking for a function that when I differentiate it 3 times and then I add 3 times the first derivative, I should end up with the function that I started with. Okay, then let me just see this. Okay, then we have what is called the solution of our differential equations. So a solution to a differential equation. So when you see DE, that's short for differential equations, or differential equation is a function y is equal to f of x, which satisfies the given equation. Okay, so when we say find the solution, we just want an equation that when you substitute it in there, it satisfies the equation. So we can look at examples of this. So again, we did this before. Even though at that time we hadn't talked about differential equations, we did examples of this. So number 1, it says show that y is equal to sine 2x is a solution to d2y dx2 is equal to minus 4y. Okay, so this is what we want to show. So this, we will substitute it in there and show that the left-hand side is equal to the right-hand side. So this is the second derivative, so we have to differentiate it twice and then work this one out. Minus 4y is just minus 4 sine 2x, and see if the left-hand side will be equal to the right-hand side. So on the left-hand side, we have d2y dx2. Okay, so this is what we want. So first we start with dy dx. So dy dx, this is 2 cos 2x, and then d2y dx2, this is negative 4 sine 2x. Okay, so that is what we have. And this, we can write -4. Sine 2x is our y that we started with. So this is -4y, and this is our right-hand side. So I'm proving it in pretty much the same way we prove our identities, showing that the left-hand side is equal to the right-hand side. Okay, so here, just to note, sine x Okay, now these differential equations, they occur in nature. There's quite a number of applications, and I always say you guys in engineering are the ones who do most of these applications. With me in mathematics, it's mostly just the theory of it, and then you guys apply it. So one place where these differential equations occur is in radioactive decay. So we have something like this, dN dt is equal to Kn, okay, where n is the number of particles that remain at a specific time. So when we say dN dt, that is the change in n with respect to time. So I want to see how many particles here. This represents the number of particles we have at a given time. And then this is the formula that people who studied this have actually come up with. And here, K is a constant. So we use this in radioactive decay. So when we talk about half-lives, I'm not sure if in mechanics you talk about half-lives of radioactive material, but this is also used in population studies. You will see this formula also when they're talking about the growth of a population. Okay, this is another example where we have to show that n is equal to n naught e to the power of kt is a solution to dN dt is equal to Kn. And here we're told that n naught is the initial number of particles. So here they're talking about parent nuclei, but it's the initial number of something. Okay, so here all we want to show is if I differentiate this equation here, it will satisfy this expression that I have over here. So we just need to work out dN dt and then show that dN dt is equal to K multiplied by N, where N is this N naught EKT. Remember, N naught is the initial number, so that means you start, if you're talking about the population, you start looking at the population today. You see how many people do I have today? That is your N naught. So your starting point, that is your N naught, your initial number. So again, here with this one, all we have to do is find dN dt. So we start on the left-hand side. So dN dt, Now here, n naught is a constant. It's if you started with 1,000 people, that is a constant. It's not something that changes. And our variable in this case is t. So we differentiate this with respect to t. So this is n naught. And then the derivative of e to the power of kt is just e to the power of kt. And then we multiply by the derivative of kt, which is k. So this is k and not e to the power of kt. And you can see that this part over here, this is n. So this is equal to k times n, which is equal to my right hand side. Okay, so sometimes when you're solving these or showing that one is the solution of the other, try not to worry too much about the words and the explanations and the whatever is said over here. So even if you don't understand what a parent nuclei is, you have to remember the mathematics of it, that I just need to differentiate this and show that I can write it as k times n, where n is equal to that. And number 3, show that L equal to cos square root of k over m times t is a solution to the oscillating mass on a spring differential equation. So again here, but I think in mechanics you deal with oscillating springs. I've never had to deal with oscillating springs and things like that, but even if you don't know what oscillating springs is, all you have to do is look at the mathematics of it. So the equation is d2L dt2 plus k over m L is equal to 0. So again, what we are interested in doing is show that when I differentiate L twice, substitute it there, and then add k over m multiplied by L, the answer will be equal to 0. So here k and m are constants. The only variables are L and t. Everything else is a constant. Okay, and the way we do it is just like we did the previous two. You have your left-hand side, you work on it, excuse me, and show that the answer is what you have on the other side. So we're working on the left-hand side. So on the left-hand side, we have d2L dt2 plus k over ml. This is what we have. So we start with dl dt. So remember, L is cos of the square root of k over m times t. Okay, everything is under the square root. No, not everything is under the square root. It's, maybe I should show it better like this. The brackets are there. The t is not under the square root, but under the square root you have k over m. Okay, so when I differentiate that, this is minus sine square root of k over m times t, and then we multiply by the derivative of that one, which is just square root of k over m. Okay, so you can simplify this and write it better. This is minus square root of k over m sine square root k over m times t. That is the first derivative. Now on the left hand side we need the second derivative. So I have d2l dt squared. I just differentiate this again. So the derivative of sine is cos. So I will have minus cos square root of k over m times t, and then I have to multiply by this again, and when this multiplies with that, I will just have k over m. So this will be equal to that times k over m. So this square root that's already outside, and then multiplied by the derivative of that will make the square root cancel, and that's why I have this. Okay, so now that I have my d2l dt squared, I can just substitute it here and then show that my final answer is equal to 0. So I have minus k over m cos square root of k over m times t plus k over m times l. L is cos square root k over m times t. You can see that these two are the same except one is negative, the other one is positive. So this is equal to 0, which is equal to my right hand side. So I have shown that k over m cos the square root of k over m times t is in fact a solution to the differential equation. Okay, so again, don't worry too much if you don't understand the scenario of the differential equation or what the differential equation is describing, whether it's oscillating springs, population growth, radioactive decay, or whatever. What you should be focused on is if it says show that it's a solution, all you need to do is differentiate accordingly and then substitute and show that the left hand side is equal to the right hand side. From there we look at the order of the differential equation. We say that the order of the differential equation is the highest order, or the highest order derivative in the equation. Okay, so if we look at this one that we did over here, this one is a second order differential equation because the highest order derivative is 2. So this one is a second order derivative. This is a first order derivative because we have only we've only differentiated once, so it's a first order derivative. Let's see, this second order, first order, same one. Okay, and then this one is a third order derivative, first order differential equation. Okay, so you just look at the highest order derivative in the equation, and then that tells you what the order of the differential equation is. So we look at some more example, d2y dx2 plus 2y is equal to 0. This is a second order differential equation. We have dy dx is equal to y squared. This is the first order differential equation. So again, what we're looking for is the order of the derivative, not the order of y. So second order because this is differentiated twice. First order because this is only differentiated once. And again, with this course, we will only be looking at solving first order differential equations. So even though some of these you can solve them, it's just out of our scope. We will not look at that. So let's look at some of the questions from exercise 5.1. Let's see. Okay, exercise 5.1. Let's do the first one. It says, show that x is equal to sine ln of t is a solution of t squared dx t squared plus t dx dt plus x is equal to 0. Okay, so that is what we want to show. And again, we just have to work on the left-hand side and then show that the answer is in fact going to be equal to 0. So doing that, I need dx dt. So to get dx dt, we just differentiate this once. The derivative of sine is cos. So I have cos ln of t and then multiply by the derivative of ln of t, which is 1 over t. So dx dt is 1 over t cos ln of t. And in my equation, I also need the second derivative. So I work that one out. So d2x dt squared. Okay, so now I'm differentiating with respect to t. So to work this out, I need to use the product rule because this is a function of t that is also a function of t, or you can use the quotient rule. Either one is fine. So I will use the product rule. The derivative of 1 over t is minus 1 over t squared, and then cos of ln of t remains as it is, and then I add 1 over t must stay the way it is, and then the derivative of cos ln of t, this is minus sine ln of t. So I have minus sine ln of t, and then I have to multiply by the derivative of ln of t, which is 1 over t. Okay, so just writing this nicely, this is minus cos ln of t minus sine ln of t, and then this is divided by t squared. Okay, so I have all the derivatives I need. Now it's just a matter of substituting them here. So it's t squared multiplied by the second derivative, t multiplied by the first derivative, add x, which is this one, and then show that the answer is in fact equal to 0. So on the left-hand side, let me just copy it. Okay, so I have t squared, then I have to multiply this by the second derivative, which is this one. So it's minus cos ln of t minus sine of ln of t. Then you divide this by t squared, and then plus t multiplied by the first derivative, which is 1 over t cos ln of t, and then we add x. So remember, x is sine ln of t. And sine ln of t. Okay, and this is what we need to show is equal to 0. So over here, the t squared will cancel. The t here will cancel. And you can see that minus cos ln of t, positive cos ln of t, those two will cancel. Minus sine ln of t, positive sine ln of t, everything cancels, and this is equal to 0, which is our right hand side. So that is how you show it. So it's just a matter of substituting, nothing particularly difficult there. Okay, then let's look at number 3. We have to show that y is equal to e to the power of x sine x is a solution of d2y dx2 minus 2 dy dx plus 2y is equal to 0. Okay, so we need dy dx, so we work that out, dy dx. This is just the derivative of that one, and to work that out, we use the product rule. So this is e to the power of x multiplied by sine x, and then e to the power of x multiplied by cos x. And then we also need the second derivative, which we're going to substitute here. So we have d2y dx2. The derivative of e to the power of, so e to the power of x sine x is this whole thing over here, because that's what we differentiated. So we have e to the power of x sine x plus e to the power of x cos x, and then the derivative of e to the power of x cos x, this is e to the power of x cos x minus e to the power of x sine x. Okay, so you can see e to the power of x sine x, e to the power of x sine x. One is positive, the other one is negative, so they will cancel. So this is 2 e to the power of x cos x. Okay, so I have my first derivative, second derivative. It's just a matter of substituting over there. So again, my left hand side, this is second derivative, 2e to the power of x cos x minus 2 times the first derivative, which is e to the power of x sine x plus e to the power of x cos x, and then we add 2y. Our y is this one here, e to the power of x sine x. Okay, and we want to show that this is equal to 0. Okay, we would multiply out the brackets, but here we can see I have 2e to the power of x cos x, and then I have negative 2e to the power of x cos x, so those two will cancel. And then here I have minus 2e to the power of x sine x, positive 2e to the power of x sine x, so everything will cancel. So I can just multiply out my brackets to show that e to the power of x cos x minus 2e to the power of x sine x minus 2e to the power of x cos x plus 2e to the power of x cos x. Then we can see this one cancels with this one. Sorry, the last one should be sine. Okay, so that cancels with this one, and then this one cancels with that one, and this is equal to 0, which is my right hand side, and then I'm done. Okay, so in the test, that is exactly what I want to see. Just substituting, work out your first derivative, second derivative, substitute, and then show that the answer is the same as on the other side. And number 5 says, what is the order of these differential equations? So we have 1 d3y dx3 is equal to dy dx, and then the second one was dy dx plus x to the power of 3 plus y to the power of 4 is equal to 0. So we just have to state the order. Here, this is a third order differential equation, and the reason why it is a third order differential equation is because here we've differentiated 3 times, so that is the order of the differential equation. Here we've only differentiated once, then it is a first order differential equation. So this is a first order differential equation. Okay, so I don't know if you'll get such a question in the test, maybe as a bonus, but it's something that you definitely need to know. Okay, now when we're solving these differential equations, the first way to solve is by direct substitution. So we have direct integration, solutions by direct integration. Okay, so here is, if you consider the nth order differential equation, dny dxn is equal to f of x. Okay, so here you can see on the right hand side I have a function of x only, so there's no y on this side. And here this is just the nth derivative of y with respect to n. So how do I get a general solution? We get a general solution just by integrating n times. So you integrate n times, then you will eventually get y is equal to some function of x. So we say that a general solution is the function y is equal to f of x, which is obtained by integrating n times. Okay, so that one is pretty straightforward. The simplest ones that you could get. If we look at an example of how we do that, let's say we have d2y dx2 is equal to x. So those are the only higher order differential equations that we'll be asked to solve. So if it's d2y dx2, then it's something that just involves direct integration, which you know how to do. So you won't get something like d2y dx2 is equal to xy, or this side it's a mixture of x and y. Again, that is out of our scope. But this one, because it just involves direct integration, then we can solve it. So I'll integrate both sides. dx2, this is, I'm integrating with respect to x. So just put dx here. So when I integrate the second derivative, I get the first derivative. So I say dy dx. This is equal to x squared over 2, and then I have my constant. Then I want to get y, so I need to integrate again. So the integral of dy dx, here with respect to x, this is the integral of x squared over 2 plus c dx. So again, when I integrate the first derivative, I get y. This is equal to x to the power of 3 divided by 6, and then plus c x, and then I have another constant here, c1. So I call this one c1 to distinguish it from that one. It's not necessarily the same constant. So sometimes we call this one c1 and c2 and so on, depending on how many times you will have to integrate. So this is the general solution. Okay, so this is the general solution. And then sometimes we are asked to find a particular solution. So I'm sure you remember when we did questions with integration, where you have to work out the constant of integration. It's pretty much the same thing, where you will be given extra information. They tell you when y is 1, then x is 2. When y prime is this, then x is this, something like that. So you'll be given extra conditions in order for you to work out this c and c1. That is called the particular or a unique solution. So here, when you just have your constant c, c1, those are the general solutions. But when you are given what is called boundary conditions, so we say that if boundary conditions are given, So again, boundary conditions, that means I just tell you when y is 0, x is 2. When y prime is 0, x is 3, something like that. Those are boundary conditions. Then then a particular or unique solution. We say YP is obtained. So YP means a particular solution where we've solved and worked out the values of our constants over here. So general solution, and then when we solve for C and C1, we have what is called the particular solution, YP, or a unique solution. Number 2. Okay, number 2, we have to find a particular solution to d2y dx2 is equal to x if, say that dy dx is equal to 0 when x is equal to 1 and y is equal to 0 when x is equal to 2. Okay, so you can see this is the same question as the one we did previously. Now we want to solve for C and C1. So it's just a matter of substituting. So we already have our general solution. Y is equal to x to the power of 3 over 6 plus cx plus c1. So that is our general solution. And now we use these boundary equations. For the first one, we say y is 0 when x is 2. So I'll put 0 here when x is 2. So 0 is equal to 2 to the power of 3 over 6 plus c times 2 plus c1. So we have 0 is equal to 8 over 6, which is 4. 8 over 6 is 4 over 3. Okay, so from here I can say that 2c plus c1 is equal to minus 4 over 3. So this is the first equation. And then I use y prime is 0 when x is equal to 1. So I go back and see what was my y prime or dy dx. This is it. So here I'll have 0 when x is equal to 1. So I'll have 0 is equal to 1 squared over 2 plus c. So we have 0. Okay, just note d that this is x squared over 2 plus c. So we have 0 is equal to 1 squared over 2 plus c, and this means that c is equal to minus a half. So now that I know what c is equal to, I will substitute it over here to solve for c1. So c1, this is equal to minus 4 over 3 minus 2c. So we have minus 4 over 3 minus 2 times minus a half This is minus 1/3. Okay, so now I've solved for C1 and C, so I can state that my particular solution is x to the power of 3 over 6 minus x over 2 minus 1/3. And the particular solution will still satisfy the original differential equation, just like the general one does. But here we don't have arbitrary constants. We know what the constants are equal to. So again, with finding the particular solution, you will just be given some extra conditions. With those extra conditions, you substitute them into your equations and then solve for the constants that you have. And that's pretty much it. Okay, then another technique that we use for solving differential equations is what we call separation of variables. Talk about separation of variables. So again, these are the basic ways that we solve differential equations. And separation of variables, we can use it when we have, say, these are first order differential equations of the form dy dx is equal to f of xy, where this function f of xy can be separated so either by division or some other manipulation. So you have, for example, f of x y is equal to p of x over q of y. So you can see the numerator is just x, the denominator is just y. So I can always have the terms with x on one side, the terms with y on one side. And then from here we see that I have dy dx is equal to p of x over q of y. So that is this. I've just rewritten it in terms of p of x over q of y. So then I say the terms with y on one side. So I have q of y dy is equal to p of x dx. And you can see here, I just need to integrate both sides. So the integral of q of y dy is equal to the integral of p of x dx. And then that will be the solution. So sometimes your differential equation is separable, and that is one of the easiest after direct integration. So let's see some examples. One says find to 4 decimal places the unique solution to this equation, this differential equation, y squared plus 4 ln of x plus x dy dx is equal to 0, and we're given some boundary conditions. So given that y is 2 when x is equal to 1. Okay, so first we must find the general solution, and we say the way to do this is to separate the variables. So I can rewrite this as y squared plus 4 ln of x is equal to minus x dy dx. Then I want all the terms with x on one side, so I'll divide by minus x and multiply by dx. So this is equal to minus, or even keep the minus on the other side. It doesn't matter where the minus is really. Minus ln of x over x dx, and then divide by y squared plus 4. So this is 1 over y squared plus 4 dy. So you can see I've separated it. This here is only in terms of x with a dx. This one is only in terms of y with a dy. So I can solve this by integrating on both sides. So this is minus the integral of ln of x over x dx. This is 1 over y squared plus 4 dy. So you can see here you need your integration techniques. So everything we did on integration, you need to bring it here with you. Okay, so the integral of ln of x over x, the derivative of ln of x is 1 over x. So I have 1 over x dx. So this is like u du. And when I integrate that, I just get ln of x squared divided by 2. So this is minus ln of x squared divided by 2. Let me keep the equals in the middle. I have too many equal to signs here. Okay, then on the right hand side, here I can tell that this, I can rewrite this as tan inverse, or I should be thinking tan inverse, but with tan inverse this has to be a 1. So I factor out the 4. So this is 1 factor out the 4, then I have y over 2 squared plus 1 dy, and then in the numerator I need a half, which is the derivative of that one. So I have minus ln of x squared over 2. This is equal to a half here, and then integral a half in the numerator, y over 2 squared plus 1 dy. So minus ln of x squared over 2 is equal to a half. This is tan inverse of y over 2 plus my constant c. And then now we want to solve for this c over here. We know that y is equal to 2 when x is equal to 1. So this is minus ln of 1, which is just 0, over 2. This is half tan inverse of 2 over 2 plus c. So here I have 0, then this is half. Tan inverse of 1 is pi over 4. Somebody's saying something, I can't hear. Okay, so this is plus. Oh, yeah, now I hear you.
What about the C on the right, left-hand side?
I took it to the right-hand side and added it.
You would say negative ln x squared divided by, yeah, if you take it to the other side, only subtract and cancel out those.
No, not if that's if you're assuming that it's the same constant, but it's not necessarily the same. So if I call this one C1 and this one is C2, here, when I add, I take this one to that side, then I have C2 minus C1. If I have a constant minus another constant, my answer is just a constant. So this constant here in black represents the constant from here included in the constant from this side. So you don't need to write two constants on either side. Just combine both constants to give one constant.
Okay.
Okay, so then we have C is equals to minus pi over 8. So I said we should write this to 4 decimal places. So this is minus 0.3927. Okay, then with this C, I will just put it over here, and that will give me my particular solution. So again, this is the general solution. And when I substitute the value of my C, then I have the particular solution. So my particular solution is minus ln of x squared over 2. And this is equal to a half tan inverse y over 2 minus 0.3927. That is my particular solution. Okay, so we'll stop here for today. Tomorrow we'll look at some of the questions from exercise 5.7 and 5.3, and then hopefully start with homogeneous equations. So remember, Friday is the test on matrices. Please prepare for that.